Welcome to this lecture on Fourier transform. We will take a look at discrete Fourier transform, fast Fourier transform, and quantum Fourier transform, and we will see the differences between them. This will be an introductory talk. We will not be going into the applications of quantum Fourier transform or the other two. And the application part will be followed in the next lecture, likely. So first, we will start with Fourier transform. So the Fourier transform of a continuous signal is given as where t is the time domain. The signal f of t is here in the time domain. And this signal is in the frequency domain. So basically what Fourier transform does is that it converts or you can say it decomposes a function into its constituent frequencies. So for this case, it will convert a time domain signal into a frequency domain signal. So a more better example to understand this is if you have a prism and if you shine light, which is basically a white light, okay, and then at the other side of the prism, what you will see is you will see 7 colors. It splits it into its constituents, which form the Webb wire. So this is the white light. So the Fourier transform basically does something similar by using a mathematical tool. Okay. Now we know in today's world we mostly deal with digital signals, so we less often deal with the continuous signals. So what we do is we basically discretize this signal f of t. So if you have a signal coming from, say, suppose even if it's an image signal or any communication system, so this signal will then be in discrete form. So then the discrete form of the Fourier transform is given as discrete Fourier transform. So if you have a signal, something like this, so what we do is we basically discretize it, or you can say we sample it at various intervals, okay, and then we can write the same signal as something like, say, suppose the values are 1, 2, 3, 4, then 3, 2, 1, something like that. So this set then represents the discretized or the sampled signal. So this was f of t, which was continuous, and this is a discrete version of this thing. Okay. So there are some rules to discretize it. You have to make sure that the sampling rate is enough so that you don't lose information. So once you have the discrete form of the signal, then the Fourier transform is given as this, where k is the index for the sample or the frequency domain sample, and n is the index for the running summation, and this big N is the total number of elements of x of n. So if there are, say, suppose 8 elements, then this big N will be 8. So this then gives you the discrete Fourier transform of this signal x of n. Now, again, what it does is basically this thing also gives you the frequency components of the signal. So if you know, if you have, say, suppose a musical note, and you do its discrete Fourier transform, what you will get is you will get the pitches in the musical note, which are basically the frequencies. Okay. So now, if we want to evaluate, say, suppose the complexity of DFT. So by complexity, I mean like how many, uh, or in simple words, I would say like how many operations I need to do in order to calculate DFT of a signal. Okay. So assuming that I have a signal with n samples, which I can write in as a power of 2 power n. Okay. Then if you take a look at the mathematical form here, so you see for each sample x of, so say suppose we are calculating x of 0. Okay. So basically, I think I should put this one as a capital one to distinguish it from the small one. Okay. So for x of 0, you see you will require n multiplications, right? So you have to do n multiplications. So you will require n multiplications. And also, if you see, you require then summing up all those multiplication you get from each of the product. So if you expand this summation for, say, suppose just 3 terms, so you will get x of 0, x of 1, x of 2. Okay. And for each term, you have to multiply it with this factor, exponential factor. And then you have to add the 3 terms, which means you will require 2 additions. So for n terms, you require n minus 1 additions. Okay. So in total, then if you calculate the total number of operations that are required to compute the DFT is, so for one of this, you require n multiplications and n minus 1 additions. So total operations per component x of k, let's say suppose, is n plus n minus 1, which we can write as 2n, assuming n is very, very large than 1. Then you have to do same thing with all the components. And if we have here n elements, then you will also have n elements in the Fourier transformed signal. Okay. So then total number of operations will be n into 2n, which gives you 2n square. So in big O notation, then we write it as the complexity grows as quadratic. Or if you put n as 2n, so then you see this represents the complexity of the discrete Fourier transform. Okay. So when you have large sample, when your n is very, very large, then this becomes quite tedious or very time consuming to calculate discrete Fourier transform by this method for a signal. So then we have a much better algorithm which also calculates the discrete Fourier transform, but the approach is what we call fast Fourier transform. So in layman terms, what it does is divide and conquer. So let's see how it works. So you see we have the discrete Fourier transform given as n equal to, then we have x of n j 2 pi k n by n. One thing to note is that sometimes I may write the imaginary number as I, or sometimes I may write it as j. So it's the same thing. Okay. Okay. So what we do in fast Fourier transform is we basically divide this x of n, our time domain signal, into two parts. So we call it the even part and the odd part. So what I mean by that is, so say suppose you have a signal which is 1, 2, 3, 4. Okay. So what I will do, you see this index is 0th index. This is 1, this is 2, this is 3. So what I will do is I will separate out the even indexed numbers and I will separate out the odd indexed numbers, which will then give me x of n. I can then write as x even plus x odd, right? So that's how we split the two. And now I put this thing into my primary equation. So what I will get, x of k equal to 0, n by 2 minus 1, x of 2r j k r by n, and plus I see a small space. Let me write it here. 2 pi k. Okay, fine. Now what I did is that I basically changed the indices here, or you can say the dummy variables. So now this component, the first one here, this thing represents the even part, because you see it's only taking the even indices from x of n. Okay, so you see r will be 0, so it will be x of 0, then 2, then 4, so up to n by 2 minus 1. And now why I have separated it? Because the total number of samples are n, so the half will be even and half will be odd. And this section represents odd. So if you put r equal to 0 here, so the first number it will pick is x of 1, right? So which is the odd one, then 3, 5, 7, and so on. And same wise, I have changed the variable here, which was n, but now it's 2r. Okay, and same wise here. So if we do a little bit of algebra, then we will have, then we can write it as this. 2 of r minus 2 pi 2r n plus now what I will do here is that I will just evaluate this exponential. Okay, so I will keep 2r by n separate and the rest one separate. So there will be two exponents. The first will be minus j 2 pi k 2r by n. Okay, and then there will be one more 2 pi k by n. Okay. Now you see this exponential here and this exponential now are the same. Okay, So let me do a little bit of more algebra. So then I can write it as r equal to 0, n by 2 minus 1, x of 2r. Okay, and now this 2, I can also write it as n by 2, right? Because we have only n by 2 samples here. So now we have a right way of representing only the even indices. And same wise, I can do here. So here I can also write 2 pi k r n by 2, and you have this one more exponential. Okay. Now what I will do is let's call this thing as x even, and this thing here, let's call it x odd. Then what we will have is x of k is x of even, okay, plus e to power minus 2 pi j by n x odd of k. Okay, now this thing here is what we call pivotal factor. Okay. Now what have I done? So you see, now I have basically divided the DFT into two parts. That's based on the indices. They are even and odd. I have divided in two. So if I try to represent it graphically, so then it will look like something like this. So I have initially x of 0. So say suppose I'm doing it for n equal to 8 samples. Okay. Or maybe just n equal to 4 to keep things simple. Then this will be x of 2, then this will be x of 1, then this will be x of 3. Okay. So you want to calculate DFT. So what you have done is you divide it into two parts. So this is a regular DFT. So this is a regular discrete Fourier transform. That's the x even for n by 2, which is 2 point now. Okay, same thing here. It's 2 point for the odd one. And then at the output, what we have is for the first one, for the x of 1 here, it will be x even 1. So this component from here, okay. And so whatever you get from here, so x even 1. So it will be, let me write it xe. So it will be xe, actually 0, not 1. So it will start from 0, xe 0. Plus when you put here 0, it will be 0. So it will be just x odd of 0. And where will this x odd come from? It will come from this line, because this is what represents the odd part. So it will be here, and here this point represents a summation. Okay. And same wise for this one, this will be then x of 1, x even of 1 plus x odd of 1. And it requires one more point, which will come from here, and you will add it. Okay. And also for the rest one, we use basically, so for the rest one, what we use is that we calculate it as, for the rest half, we remember this property. X of, no. I seem not to remember this one, but okay, let me do it this way. So we have a pivotal factor. If you have Ej 2 pi kn by n, okay. 1 minute. Yeah, and now to calculate the rest of the components, which will be the rest of the half, you will have to put as k here as 2 pi n, k plus n by 2 by n, which will give you 2 pi n, k by n, and then there will be one more, which will be 2 pi n by n into n by 2. This will go out. 1 minute. I think there is something wrong. Oh, sorry, there is no n in here. Okay, sorry, this thing is not here. So it will be just e to power I pi, which is -1. So your total factor will be then minus I pi k by n. Okay, so for the rest of the components, say suppose for x of 2, you will have to use we'll use x e of 0 minus x e of 0. So the minus basically here you will also have a pivotal factor. Let me call it as w. So a small w you will have here also. Okay, and here it will be w0, which is 1. And same wise for x of 3, then you will have x of 1 minus x0 of 1, and this will come from here. So it requires x of 0. It will be summed here, but you have to multiply it also by -1. You have to multiply it also by -1, and for this component, same wise. So this then gives you the decomposition in terms of the fast Fourier transform. So same wise, then what you can do is, so if you want to further decompose this one, okay, so you again basically divide these components into even and odd. So what I mean by that is, so say suppose if you see our x even signal here, okay, so our x even signal is composed of 0 and 2, but you see this, if you just represent, if you just see this index, this is a 0 index, this is a 1 index. So you can again split it into even and odd, and then do again with this thing. So there will be not, so in the next step there will be again one more, so there will be just one point DFT. So you can again open it up, so there will be something like this. Okay, so then finally when you reach the 1 point, you get a structure which looks something like this. Let me show it for 8-point DFT. One more. So here, when you do, so for n equal to 8, for n equal to 8, first division will be 4 and 4. So 4 will be positive, and sorry, 4 will be even and 4 will be odd. So you will have to 1, 2, 3, 4 like this. You will have these butterfly kind of structures. Okay, and you will also require -1 here, and from here you will also require lines like this. Okay, so this is the first section. In the second section, we will again have 2 and 2. So here it was 4 and 4. Then you will have here 2 and 2, which will look like this. And this. And then here you will again divide this section into 2 and 2, which will look like this. Okay, and then finally here, now then you will have 2 and 2. So it will be like this until you reach a 1-point DFT, which you can compute easily. Okay. And here you will have x0, x1, x2, 3, 4, 5, 6, and 7. Okay. And from here you will get the capital X's, though they will not be in the same order like 0, 1, 2, 3. Okay. You will have different I's and J's. Okay. So this way, then you can compute the discrete Fourier transform of a signal very much efficiently. Now, let's see what is the advantage of doing this. Like, why do we divide and compute each section separately? So that is obvious when we compute the complexity of fast Fourier transform. So for fast Fourier transform, we see initially we split n point DFT into 2 n by 2 point DFTs. Okay. So if you see at each level, you will have to compute n multiplications. Okay, which is by multiplication. Where does this multiplication come from? It's because of this, the two factor. You need to multiply it to the odd one, and then you have to add it. Okay, so there are n multiplications and there are n additions. Okay, and how many number of stages will be there? So you see, for n equal to 8, how many stages we have? We have 3 stages. Okay, one, this is the first stage. So this is the first stage, second stage, third stage. Okay, so we have 3 stages. So for in general, if you have a n point DFT, number of stages is log 2n. Okay, then if you see the total number of operations, so you have initially n multiplication plus n addition, which is 2n, which is still n in the big O notation. So the total number of operations then are n into number of levels. So number of operations per level into number of levels. So number of operations per level are n, and total number of levels are log 2n. So this is then the total number of operation. So if you just write it in the 2 base 2, then this will be 2 power n, 2 power n. So now you see there is a significant reduction in the number of calculations required to compute DFT of the same signal when done with TFT. So if you use direct DFT, your complexity is 2 power 2n. Okay, and with FFT, if you compute the same signal with FFT, your complexity is n to power n. So there's a significant reduction in this. So that's why so you'll see most of these real-time systems, they basically implement fast Fourier transform because it gives a speed up. Okay. Now the question is, can we do something so that we can accelerate these computations further? Okay. So now what we can do. So is there a way to do the same computations on a quantum computer? Can we develop some kind of algorithm, quantum algorithm, which can help us achieve more speed up than what we can get from the fast Fourier transform? So let's take a look at now what's called quantum Fourier transform, and let's see what it can do and what it cannot do. Now, so just like discrete Fourier transform, uh, we have a same expression for quantum Fourier transform, but the difference is the representation. Here we will use Bryant-Katz, which are most common in quantum computing notation. So let me first write the DFT, which is written as okay. So DFT we write as x of k equal to 0. E to power j 2 pi n. Okay. Now in quantum Fourier transform, so if you have a state, say suppose j, okay, if you want to compute its Fourier transform, or say suppose this is state k, okay. Okay, and let's say suppose its Fourier transform is some state j, okay. Then this is written as n e to the power 2 pi I j k n k. So this is the way we write the quantum Fourier transform of some basis j, okay, of some basis k. So now these represent basically the, you can say these represent the amplitudes, and 1 minute. And the factor here, 1 divided by root over n, is the normalization factor. Now let's try to basically expand it and try to give it some different shape so that we can make a circuit out of it and compute it on the quantum computer. So first, we know we will represent it in terms of in the basis of in the power of 2 to the power n, where n is some integer. So let's assume that we have bases 0, 1, 2, so on up to 2 power n minus 1. Okay, for a n qubit quantum computer, right? Then let's do one thing is that instead of writing it as 0, 1, 2, 3, we will represent them as bits. So what I mean to say is that for n equal to say suppose 3, I can write the bases as 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, and 1, 1, 1. Okay. And if you want to convert any one of them back to the decimal notation, you know it's done. So any j can be written as j1 2 power n minus 1, j2 2 power n minus 2, and so on, jn 2 power 0. Or in more compact form, you can write it as l equal to 1 to l equal to n jl to n minus l. Okay. So this is the binary conversion back to decimal. And same wise, 1 minute. So the decimal, so the notation that we will be using in general will be J1, J2, J3. Okay. So this will be the general notation. And same wise, if you have a decimal point, so then we will use I mean, if you have a binary fraction, so then we will use the notation J1, J2, so on and so forth up to Jn. And a way to convert it back to the decimal is this can be converted back to decimal as JL by 2, JL. So if you have J1, J2 by, sorry. So this will be written as J1 by 2, J2 by 4, plus J3 by 8, and so on. Okay, so this is a way to convert the binary fraction back into the decimal. Okay. Now, let's try to evaluate our expression for quantum Fourier transform. So it was root n a equal to 0 for n minus 1 to power I jk by n. Okay, now what we do first is let's replace n by this 2 power n. Then we will have pi ij power n, and for k, let's write it as k. Okay. In the next, what we will do is, since I said that we will represent each of the bases here as a binary, so we can expand it also then as a binary. We can write it in the binary notation, which will give us a1 to 1, a2 to 0, so on and so forth up to kn01 e power 2ij to n. So here I can write then at k1, k2 up to kn. Okay, so what I did is that I opened up this summation and this notation here as a binary representation. Okay, so also what you could write as 0, 1, 2, 3, now we can write as 0, 0, 1, 0, 0, 1, or 0, 1, 0, and so on and so forth by using all these summations. So you will get the same thing as is written here. Okay. Now we also need to look at this k here, which is in the exponent. So we have changed the k in the basis. We also need to change the k to binary representation in the exponent here, in the exponential. So let's try to do that. So that should give us so we will have these summations k1, kn 0 to 1, and then we will have e to power 2 pi ij. Now this k here is in decimal notation, right? We need to write it as a binary notation. So we just saw how we can write any number as a binary notation is using this summation. Okay, so let's plug this thing here. So then we will have, let's say L equal to 1 to n, KL 2n minus L, and we have then a little division here by 2n. Okay, so this all of this thing is in the exponent. Okay, this all things in the exponent, and then we have k1, k2, kn. Okay, now if which finally gives us j. Oh, I wrote it twice. This is only one I here. It is, oh no, it's, oh, sorry. Excuse me. This j represents this basis. Okay, so it's 2 pi ij. So I here is the imaginary number, j represents this. Okay, the basis. So then we will have summation L equal to 1 to L, KL 2 minus L. Okay, and then we will have K1, K2, and so on. Okay. Now what we can do is, you see this exponential here. If you take a look at this exponential, so this is something 2 pi I j, then this is something like K1 minus 1, it's K2 minus 2, and so on, which I can also write as e to power 2ij K1 2 minus 1, then 2 pi ij K2 2 minus 2, and so on. So a summation here can be converted into the product of the exponentials, right? So let's try to do that. So what we will have is okay. So let's this represent the product for L equal to 1 to n terms, because we have here L equal to 1 to n terms. So all this summation will now be converted into the product. So what we will have now here is KL 2 minus L, and we can just also write here KL. You don't now need to write K1, K2, because you can anyways then accommodate that into the product, right? So this is then what we will get. Okay. Now, since we can move summation and this product back and forth here, then we have and I can write it also as KL equal to 0 to 1 e to power 2 pi ij KL 2 minus L, and then you have KL. Okay. Now to see what I have done here, let me give a small example. So say suppose what I have is two summations. Okay, let's say suppose I have summation for K1, summation for K2. And to take a simple example, let's say suppose I have some exponential of KL and KL. Okay. Now, no, sorry, product is also there. Okay, for two terms for simple. Let's say suppose L equal to 1 to 2. So if I first apply the product, then summation, then what I will get is, then I will have is e to power K1. So if I apply first the product, then I will have e to power M1 K1 and e to power K2 and K1 K2. Okay. And then after this, if I have to apply the summation, then this will form 0 plus 0, 0, 0, 0 plus 1, 0, 1, and so on for other two terms. That's then what I will get. But if I take this product out and use the summation first, then what I will get is first is e to power 0 k0 plus e to power 1. Okay, and then there will be a product also L equal to 1 to 2. So finally, I will have, when I evaluate it, this will be like e to power 0 plus e1 e, oh, let me show it on the next page. So if I evaluate it, what I will then get is something like this. Okay, now if you again just evaluate it, do some algebra, you see it will be again 0 0 0 plus 1 0 1 and so on. So that's same as what I have got here. So it does not matter whether, I mean, in this case you can just move the product and the summation back and forth. So if I do that, what I have is then this expression in the end. Now what I want to do, let me keep the product as it is. Now let's evaluate this thing here. So if I just QKL equal to 0, so this whole exponential will be 1. What I will have here is just 0 and then 2 pi ij 2 minus L, and you will have 1. Okay. So this is what I would get then. Okay. Now let's try to expand it a bit more. So how do we do that? Let's try to see that. Now, if you see this exponential here, this thing, so you have e to power 2ij by 2L. That's what it is. Okay. Now J will have its own representation, like I said. Okay. So say suppose your J is a 3-bit number, which will give you 2 power 0. Oh, wait a minute. Forget it. Okay, so it will be J1 2 power n minus 1, J n minus 2, 2 n minus 3. So for a 3-bit, it will be J1 2 square, J2 2 plus J3. And if you, I mean, the J1, J2, J3 can be bit 0 or 1. Now you are dividing it by 2 power L. Okay. Now assuming 2L, now, okay. Assuming your L is 2, then what will be J by 2 power 2? So you will have then J1, you will have J2 by 2, and you will have, okay, for the simplicity, let me first show J equal to 3 to keep things a bit simple. So it will be uh, this will be square, and J3 will be cube. So this, you know, is a representation of a binary fraction. And this thing I can write then as J1, 0.J1, J2, J3, right? Which I just showed here. You remember somewhere here? Here, yeah. So this, whenever you have a representation like this, then you can write it in short like 0 point J1, J2, J3, where J1, J2 are the binary bits. So moving on, then if you now have L equal to 2 or 1, now if you have L equal to 1, say suppose, then you will have J1 2 square, J2 2, J3 1, and you are dividing it by 2, which gives you J1 2, J2 plus J3 by 2. Now in this case, how we will write it in the binary fraction representation. So if you just see, you just put all of this thing just into the exponential to understand it better. You have 2 pi I Now for j, you will write j1 by 2, j2, j3, j3 by 2. Okay. So this whole thing j by 2l, you put it equal to this thing for l equal to 1. Okay. Now, if you see, the first term will be 2 pi I j1 2. Then second term will be 2 pi I j2. The third term will be 2 pi I j3 by 2. Okay. Now I is an imaginary number. J is either 0 or 1. So assuming it's 1, so you will have e to power 4 pi I, which is 1. Same wise here, you have j2 can be 0. If it is 0, then it's 1. If it is 1, then still this is 1 because this is a even exponential, complex exponential. It will be again 1. Now, what about this one? So this here is 2 pi I j3 by 2. Now, j3 can be either 0. If it is 0, then fine, then this will be 1. But if it's not 0, it's 1. Here is uh, 2 pi I j3, which you can then write as 0.j3, right? Because this is now just j3 by 2. So j3 by 2 means you are just representing the fractional part for this bit j3 here. So you will just write it as 0.j3. In the previous case, you had the fraction in all the bits. So they were all being divided by power of 2. So it gave out a representation 0 dot j1, j2, j3. But here you see the j1 and j2 basically contribute to 1 to the overall exponential, so we don't count them. So only the bits which have a power of 2 in the denominator, those only contribute to the exponential in the fractional form. So 0.j3. So keeping this in mind, then we come back to here. Now let's see what we have to do from here. So if we now try to open up this product, okay, so then the first term will be two by I j by 1. Okay, so the first term will be for L equal to 1. It will be j by 2L. So it will be this one. And then you have 1. For the second product term will be e to power 2 pi I j by 2 square, and then you have 1, and so on up to n. Now here j, j has a representation something like this, and you are dividing it here by 2. Okay, so 2 means if you see the last term, so if you again go back to what we saw here, somewhere here. Okay, so when you will divide all the terms by 2, so they will still have a dominating term in the numerator. Okay, so it will still have 2 to the power n minus 2, in which is a dominating term. Only for this term here, jn, this 2 raised to power 0 is 1, so you will have a jn divided by 2. So all these terms will contribute to 1. This will only contribute to the fraction. For j square, this term will contribute to jn by j square, and then the jn minus 1 will be divided by 2. So those two will contribute. So same way, then we can write this thing here as plus 2 pi I 0.jn, and the second term will be e to power 2 pi 0.jn minus 1 jn, and you will have 1, and so on and so forth till the last term will be 2 pi I 0.jn. J1, J2, Jn1. Okay, because in each of the product terms, the denominator in the power of the denominator in the 2 will keep on increasing. So you will be adding more and more of these fractional terms here. So this then represents the Fourier, the quantum Fourier transform of a basis. Okay. Now the product representation. Why the product representation? So the product representation basically helps us make a circuit to compute quantum Fourier transform on a quantum computer much more easily than any other representation. Now let's see how we can use this representation to basically uh, implement it on a quantum computer. So let's now look at that. So before that, I would like to introduce a gate, RK gate, which is given as, okay. And if you have a controlled RK gate, so if you have some controlled RK gate, then that will add the phase to only then that will add the phase only when you have one computational basis and not to when you have zero computational basis. Okay, so let's try to make a circuit and then things will become much more simpler. So a way to do it is, say, suppose, so now we had J, okay, so if you see the final expression, we have J, but you can give it a binary representation also, right? So for the circuit, we will give it a binary representation. So we will say J1, J3, and okay, should not write more, so on and so forth up to Jn minus 1 and Jn. So the quantum circuit for implementing the quantum Fourier transform is given as, yeah, I should first draw these lines to be better. Okay, that will be complicated. Okay, let me draw it one by one. H R2 Rn minus 1 Rn, which will give at the output 0. Oh, there's small space, so I will have to accommodate it. E power 2 pi I 0.j1 up to jn, and you have this little one here also. And then for the second one here, this will be controlled gate, and then you have H. Then this will be R. Need a small space. I will try to see if I can accommodate it. Rn minus 1. And then you will have the same thing that's here, but this time there will not be so in the exponential, I will just write the exponential term only. Okay, so there is a 0 added to it and multiply it by 1. So here this time it will be just 0.j2 to jn. Okay, because j1 is not a part of this bit here in any way. Okay, and then same wise, the last one will be H R2, and for the last one we will have only exponential 2 pi I 0.jn minus 1 and jn, and finally for the last one we will have only just Hadamard gate, which will give us an exponential 2 pi I 0.jn, and there will be these controlled gates like Rn minus 1, which will go to this thing, Rn will go to this thing. So the way I have constructed it is that for each of these controlled gates, it's controlled by the index, so RK. So you have to connect it with the kth bit. Okay, and there is a Hadamard gate in front of all the lines before you pass them through these RK gates. Okay, so same wise here, Rn minus 2, and so same wise this thing will go to here, and Rn minus 1 will go to here. Okay, so it's being connected to the lines below them. I will try to see after this lecture if I can find online some good circuit for this one. I will try to show it in a better way. So now let's try to focus on these binary fractions. So if you see for the first one, you see this R2 is connected to J2, then there will be R3 which is connected to J3, Rn minus 1 to Rn minus to the n minus 1th bit. So that's why in the exponential here you have all these fractions like J1, J2, J3. Okay, because what it does is so if you try to take a look at the circuit mathematically, so for the J1 bit, you pass it through the Hadamard gate. Okay, so you know Hadamard gate can also be written as quantum Fourier transform. So if you have like say suppose 0, you know you can write it as when you pass it through the Hadamard gate, you get something like this, and if you have 1, you pass it through Hadamard gate, you get something like this. And it's the same thing we can write also as quantum Fourier transform. I have also shown it in some previous lecture, I remember. So it will be J1, 1, root 2, and you can write it here also J1, 1 by root 2. So for this case, if you see the J1 will be 0, you can see the bit is here 0. So this will be all 0. So you will get back this. For 1, this will be 0.1, and you know 0.1 is equivalent to 1 by 2. That 1 by 2 and this 2 will go off. You have just exponential of e power I pi giving you -1. So you will get back this. Okay. So then here for a general bit J, when you pass it through the Hadamard gate here, what you will have is square root of 2 plus 2 power I 0.j1, and you have this thing. Okay, so at this point, so what I'm writing is for this point here, the output at here, okay, output here. So Hadamard for J1, and you see all the other bits are same as they are at this point. So you will write them as they are J2, J3 up to Jn. Okay. Next, what you do is you pass it through the R2 gate. Now, what's R2 gate? Like I said, it just adds a phase. So since it's controlled R2, so it will add a phase 2 to power I, 1 minute, yeah, divide by 2 square, right? Now what's, so if you see clearly here, you have in the exponential 1 over 1 by 2, which you can write as 0.0 J2, right? So if you then add it, so when you apply this R2 gate to this qubit here, which I mean to say this, so whatever is the state here, let's call this state as psi1. Let's say this is psi1, and now you are passing this psi1 state through a controlled gate R2, which will not act on 0 state, but on this state. So then let me write the output at psi2. The output at psi2 will be then 0, 2 pi I, 0.j1, and it will RK1, R2 gate in this case will add 0.0 J2 here, and you have this thing here. Okay, and you will have rest of the things as they are, Jn. because you are not doing anything with J2 again here. So they will stay as they are. So what you will have as psi 2 is 2 pi I 0.J1 J2. And you have J2 Jn as it is. Then if you'll see, you then pass it through R3 gate here, right? So if you see when you pass it through H gate, you got 0.J1 here. You pass it through R2, you begin to get 0.J3. So same wise, when you will pass it through R3 up to Rn, you will get all the binary bits here like J1, J2, J3, J3 up to Jn till you reach the end of this line here, and that's where you have 0 point. You have 0, which is we have already here, and then you have all these 0 point J1, J2 up to Jn for the first bit. Now for the second bit, if you see, you pass J2 through Hadamard gate, so it starts with J2. So there will not be J1 because it starts with J2. Okay, so that's why you see then you have J2 down to down to Jn. Same thing with J3. It will start with J3 passing through Hadamard gate. So you will have the first one as J3 in the exponential, and then down to Jn. And finally, for the last one, since there is only H gate, and there is no OR gate after it, so you will have only last one as Jn. Okay, so you see at the out of each of these lines, what you have is you have, if you carefully look, you have these multiple terms where you have exponentials having starting the binary fractions from J1 to Jn and finally only Jn. And if you compare it with the quantum Fourier transform, okay, somewhere I wrote it here. So if you see, they also have the same representation. So you have the first term with only 0.Jn, then you have Jn minus 1 Jn, and then finally the last term here is 0.J1 to Jn. The only difference here is that here we have the first term as this one, and here we have the first term as 0.J1 to Jn. So you can use some swap gates to do that. That's not a big thing to do. So this way, then we see then at the output, what you have is then the quantum Fourier transform, right? Because you can then carry out a tensor product of all of these, and then at the output state, which you can write. So if I represent the first line, say suppose as so the output of the first line, let's say it's say suppose K1, and this is K2, blah 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 up to Kn. Then at the output, what I will have is, let's say psi output will be then K1, K2, K3 up to Kn, which after using swap gate will give you the same expression that I just noted, including the normalization, that you have 0 plus Jn 1 and so on and so forth up to the last one. So this way we can then compute quantum Fourier transform on a quantum computer. Now let's try to calculate the computational complexity of this algorithm. So to compute that, if you see, so the first line, if you see, it requires one Hadamard gate, okay, followed by n minus 1 OR gates, right? So you have one Hadamard gate and n minus 1 and you require n minus 1 OR gates. So in total, you required n operations. And the total number of gates required are n. Okay, so for the first two line, so for the, let's say suppose some random jk, you require for the first one. Okay, let me write it that way. Do not confuse. So for the first one, you require one Hadamard gate plus n minus 1 OR k gates, giving you a total of n gates. For the second line, you will have you will have one OR gate less than the previous one. So in total, you will have for J2, you will have n minus 1 gates, and same wise for J3, you will have n minus 2 gates. Finally, if you reach the last one, you just have to apply 1 gate. Okay, 1 gate. And if you just sum it all up, like if you carry out a summation of all these total number of gates, so it will be like 1 plus 2 plus 3, so on and so forth, up to n minus 1, n minus 2 plus n. And if you remember, this is all equal to the total number of gates, then is equal to n into n plus 1 divided by 2. So you see the total gates are of the, if you write in the big O notation, that's equal to n square. And even if you include the swap gates, they will be just n by 2. So in total, then you can say it's n into n by 2 plus n by 2. Okay, so still it is O(n) square. So you see, this circuit provides a lot of speed up than as compared to what we have from the DFT and the fast Fourier transform. So now the question is, okay, before that, let me write a comparison here. So for DFT, complex T, FFT, and QFT. So for DFT, we had 2 power 2n. For FFT, we had some speed up. And for here, now we have n square. So it's not even exponential, it's just a polynomial. But now the question is, can you then use this quantum Fourier transform to calculate the classical discrete Fourier transform on a quantum computer to give you some speed up? So sadly, it turns out, no, you cannot do that, even though there is a speed up, but you cannot do it. So the reason for that is that the amplitudes for this, that the state you have to prepare. So the way, if you want to calculate the classical Fourier transform, so you will have to prepare a superposition state. Okay, so that's where it gets complicated, because you cannot access the amplitudes of amplitudes of the superposition state in a quantum computer by measurement, because whenever you will try to access them, there will be decoherence. Okay, so in general, what I'm saying is that it's not possible, even though we have a speed up quadratic from QFT, but it's not possible to use it for computing the classical DFT, because we cannot access the amplitudes in the superposition state directly by measurement. Well, that then leaves us with two responses, that either QFT is of no use to us despite its computational power, the computational speed up that this algorithm can provide, or we can find some other problems which can be solved by QFT but not by classical computers. So some of those problems are like, which is famously known as Peter-Shor's algorithm. So Peter-Shor's algorithm is based on QFT, which can be used to basically factor prime numbers. Now, why is this problem very important is that if you see all the security systems in the world, they basically rely on some cryptographic algorithms which are dependent on prime numbers. And it's known that you cannot factorize a prime number in polynomial time. So the keys that are used for these for these algorithms, cryptographic algorithms, they basically depend on these prime numbers. And since there is we don't have any efficient algorithm known to factorize the prime numbers, so basically these algorithms become then resistant to any external attack, and thus we have the security of these digital systems. So the best algorithm that is known to factorize prime numbers has a computational complexity of exponential of n 1 by 3 log 2 by 3n. So this is the computational complexity uh, uh, of an algorithm which is called a number we'll see you, I guess. So this is an algorithm, the best classical algorithm known for factoring the prime numbers, and you can see that it basically has an exponential computational complexity, thus making it very complicated to factorize the prime numbers. However, the same task when you try to evaluate on a quantum computer, then it only takes n square log n log n complexity. So then you see the computational complexity drastically reduces from exponential to quadratic and log. So that's where then we have a speed up on quantum computer. So while for now, this algorithm cannot be implemented on a quantum computer because there are issues with the current hardware we have. So, but in near future, when we have quantum computers which are resistant to external noise, then this algorithm can be implemented and we can factorize very large numbers, which are not possible with the current state-of-the-art supercomputers. So this is one such application of the quantum Fourier transform. And apart from it, there are many other applications which also include like order finding a problem or phase estimation, which we will see in the next few lectures. So that's it for today. If you have any questions, please feel free to ask. Thanks.